All right. Welcome, everybody. My name is Amit. Here with me is Pulkit. Today, we're going to talk about large-scale time series feature aggregation system that we have built using Apache Spark and some other tech. So I'll start with the agenda of the talk. I'll start with the motivation first of why we built this thing, discuss some of the technical challenges we encountered, and then deep dive a little bit into the architectural components of the system. We'll also highlight the role of Spark in the architecture, and finally summarize our key achievements. So let me start a little bit about our team. So as I said earlier, we are a team within the risk platform. I manage that team. Pulkit has been the technical lead on the feature aggregation system. So our mission is to build a scalable, self-service feature engineering platform for predictive decisioning, which in our case is based on both machine learning as well as handcrafted business rules. Feature engineering in this context means the use of domain knowledge, so fraud-specific knowledge, to create features which are then fed into the machine model. We wanted the platform to be self-service, which means data scientists and analysts can easily onboard features with minimal reliance on engineers. The platform is generic in nature, which means although we are targeting risk as the primary use case, we are currently working to contribute our work to the wider efforts, ML efforts at Uber. So let's start with a sample use case within risk. So the goal here is to detect and prevent fraudsters from taking trips in real time. Typical situations involve payments type of frauds where fraudsters will make use of stolen cards to take a trip, or they may just figure out ways to dispute the charges associated with the trip. Another type of fraud involves promotion abuse. So fraudsters may create like fake accounts, make fake referrals, and try to claim the promotion money that's being offered. So one of our observations is that in a lot of features that we need to build to detect fraud, a lot of them involve some sort of time series aggregations. So as an example, number of trips over the last X hours, weeks, trips canceled over Y number of months, referral count over the lifetime of the user, so on and so forth. So it was clear to us that we needed to build some sort of time series aggregation infrastructure to make it easy for our users to create and onboard features. So what were the requirements in front of us? So the first was around creating lifetime aggregations. So these are aggregations of all the events that have happened over the lifetime of a user. So this is multiple years. Other type of aggregation is over longer windows of time, like months or weeks or a few days. And so we would actually need to aggregate over a moving window of that duration. Similarly, we also care about short window aggregations. So aggregations over the more recent time period, basically like minutes and hours. The other requirement was that we wanted to build the aggregation system to be as real time as possible, because it is very important, especially in fraud, to be taking decisions on the latest state of the world. So since time series aggregations is a fairly well-researched area, we decided to first explore existing solutions, starting with, say, the data warehouse that we have at Uber, Hive. So Hive queries scaled fairly well, but they simply did not meet the latency and freshness requirements that we were looking for. We explored streaming aggregation solutions too, and while they worked well for shorter windows of time, they didn't, in our experience, work well with long windows or lifetime aggregations. We also explored the use of indexes in databases. So all the operational databases at Uber use some sort of NoSQL distributed stores. So we were looking for solutions, indexing solutions in these data stores. And while the query performance did improve because of indexes, it still wasn't good enough for our production needs. So what we realized is that there is not one solution out there that fits our use cases. And secondly, the onboarding steps were pretty complex for our end users, basically our data scientists and analysts. That is when we decided to sort of build our solution. But we did encounter several technical challenges. The first one was around scale. We were dealing with potentially thousands of aggregations over hundreds of millions of business entities that we deal with. So the riders, the drivers, the trips, the restaurants. And so we were, there was a huge continuous computation and storage cost involved here. Long window aggregations, as I mentioned earlier, were slow in spite of using indexes. So they would take seconds, and seconds is just way too high. What we were looking for is milliseconds level performance, low double-digit millisecond performance at a very high QPS, so thousands of reads per second. The third complexity was around something that I mentioned earlier. There were way too many moving parts. So how do we simplify the system so that to the end user, it is easy enough? So we had to figure out a way to do that. And finally, the one big problem was how do we recover from errors accruing in the aggregations? So one of our observations is that in the real-time world, many times you may end up with redundant events, duplicate events, lost events, out-of-order events, and that can mess up your aggregation value. So how do you recover from this aggregation, like the error? So this is the approach that we took. We decided to make our solution a one-stop shop. That means that there'll be a single system that our users would interact with, regardless of the underlying complexity, the subcomponents. There will be a single spec that they would use to onboard their features, and the system would automatically generate snippets of code or reconfigure the underlying components behind the scenes and completely hide the complexity from the end user. The way we made our solution scalable was essentially leveraging the scale of the batch system. And this is what the talk is primarily about. This is what we use Spark for. And this is used to compute aggregations over long windows of time. What we then do is to combine the aggregations computed through the batch system with the real-time aggregations that are running over the recent window of time to achieve the level of freshness that we are looking for. The third very important design decision that we took was to use roll-ups in the aggregations, which means all our aggregations always get rolled up over a fixed interval of time, fixed buckets of time. So by default, in the batch system, we roll it up over like a day, and in the real-time system, we use 5-minute intervals. This has serves a couple of advantages. The first is that it lets us incrementally compute aggregates, and the second is that it dramatically speeds up the query performance, because you're no longer running queries over the raw events, which typically take seconds. Instead, you're just querying over the already rolled up aggregates. So this is the key reason we were able to reach like millisecond level latencies at a high throughput. The caveat here, of course, is that we use summable functions. So things like sum, of course, and average, count, min, max. But whenever non-summable functions are needed, like percentile or count distinct, we plan to support the non-summable approximate counterparts of those functions. The way we achieved self-healing is essentially using the batch system. So our batch system is continuously run in the background, which means that any errors that accrue in the real-time world, the batch system automatically heals within a few hours. So it is able to automatically correct any aggregations in a few hours. So that is how we achieve the self-healing of the system. With that, I'm going to turn it over to Pulkit, who's going to dive deeper into the architecture.
Thanks, Amit. Hello, everyone. So before we jump on to the architecture, let us try to identify some of the parameters that are needed to compute an aggregated feature. The first parameter is the data. Now, this data in the offline ecosystem is stored in Hive, and in the real-time ecosystem, it comes through streaming Kafka events. The second parameter is the aggregation function. We currently support only summable aggregation functions like sum, count, average. The third parameter is basically the duration of the aggregation function. We call it as an aggregation window. Now, this can vary from lifetime, which is primarily the duration the entity first onboarded onto the Uber platform, and it can go all the way to minutes, hours, or even years. Now, another parameter associated with the window size is what we call the grain size. This is the granularity on which we try to roll up the events. So for real time, we try to typically roll them up to a 5-minute granularity, and for offline, we try to roll them up on a day's granularity. Now let us see how we have designed this entire system, which takes all these input parameters and try to compute an aggregated feature from there. So fundamentally, the system is built on top of 3 pillars. The first pillar is a set of Spark apps which try to compute offline aggregations. Now these aggregations, they go from days to several years. Now all these Spark apps, they operate in 2 modes. The first mode is the bootstrap. What that basically means is anytime we discover a new computed aggregation feature, we basically have to compute the entire history of that feature. And the second mode is incremental. In this mode, what we do is we try to go after the daily entity change logs, and we try to roll up the events for that. The second pillar is the real-time aggregator. This is a streaming job, which basically helps us in computing events which are shorter durations of time, typically less than 24 hours. The third pillar is our feature access microservice. We have written it in Java. What this basically enables is to seamlessly join the offline counterparts with the real-time values so that the end feature just is perceived as a single value to any upstream services that call our solution. All the features which are computed, they are stored in our feature store, which in offline, it maps to Hive, and for real time, we store all this data in Cassandra. Now, deep diving into how our offline aggregation engine is built, it is in essence a series of Spark apps. All these Spark apps, they try to go over data, historic data, which is stored in Hive in date partition tables. When the computation job first discovers a new spec, it tries to go with the bootstrap mode. What this basically means is we'll try to go after the entire history of the feature computation. The first subtask in this job is a feature extractor, which is primarily trying to extract the columns which have been documented in the query. From the feature extractor, the data moves on to the second operation, which is a rollup generator. So what this necessarily means is that if the operation is sum or count, we try to roll up those events into those buckets. So from rollups, we snapshot the data. So snapshotting is basically a process wherein we preserve the entire computation that we have done into our offline feature store. We will see how these snapshots, they help us answer some of the ML questions in the following slides. So once the computation job finishes, the optimizer picks up. What the optimizer job's role is, it tries to identify optimizations across several computations that we do. Like as we mentioned, we try to compute lifetime features and daily rolled up features. So there are certain optimizations that can happen on this data. We'll cover, I think, a few later on as well. So once the optimizer has computed these optimized data sets, the dispersal job picks up. And the goal of the dispersal job is to make all this offline computed data available in our real-time feature store in the most optimal manner. So at runtime, when one of our upstream systems, an example is a decisioning system, queries us for a feature, the real-time feature access service, based on the feature spec, it tries to join together relevant parts of the information in the feature store to return a single value. So quickly taking a glimpse on how this entire data is stored in our offline ecosystem. So on the left, yeah, it's on the left, yeah. So on the left, you will see all the data is stored in the source tables as date partitions. So from there, the computation job forks off potentially two flows. The flow on the top is basically the flow when we have to compute lifetime features. So what we do there is we snapshot lifetime features for every entity for every day. The bottom part is basically the incremental computations that we do on the entity change logs for the events that happen on a day. Now, one point worth mentioning here is that even though we capture the full snapshots for lifetime, we are not computing them every day. On the right, you can see is the output of a optimizer table, optimizer job. What it does is it tries to join relevant parts of the lifetime snapshots with the daily incremental jobs so that to the end dispersal job, there is a very simple table that it has to process and take that entire data into Cassandra. Now, going over how Spark helped us in building our solution. Using Spark, we were able to achieve massive scale. We were able to break down all our offline computation into a series of ETL pipelines, with Spark being the orchestrator. What that means is that using Spark, we can track metadata associated with the job, like what is the progress on the computation part, what is the progress on the optimizer part, and what is the progress on the dispersal part. Now, additionally, what we can do is we can also track progress there. Now, if you imagine, we are talking about billions of events that we are processing as part of a bootstrap. Now, if the job fails in the middle, we want to be efficiently able to recover from the point where the computation or any of those jobs failed. So another aspect that we saw was when we are dealing with different data sets, which are typically varying over sizes, we were reaching the file size limit on the name nodes on HDFS. To address that, we use Spark to compute dynamically the partitions or the files that are needed per partition for each day computation that we do. Spark has also enabled us to do several optimizations. One such optimization you can see is on the right-hand side. This is a code snippet from our optimizer. What it does is whenever we do a bootstrap computation, it tries to join the daily computed buckets across, I'll say, hundreds of partitions and tries to generate a table which has all this data combined. What this enables us is when the dispersal decides to disperse these features, it can efficiently checkpoint the progress, knowing precisely what entities have been processed at any given point of time. Now, when we talk about billions of events, one of the biggest challenges is how can we ensure that we can compute or we can disperse all the data only once. Spark has an inbuilt support for hash partitioner. What it basically allows us to do is it allows us to break the entire data sets into consistently hashed partitions so that at any given point of time, we can keep a track of how many partitions have been processed successfully, so that in case of a failure, we can just process from that point onwards. Spark also has helped us considerably in our dispersal ecosystem for all these features. Now you can imagine when we are computing these offline features, we typically use thousands of executors to make the computation scale. Now imagine if all these thousands of executors, they go against the real-time feature store, they can for sure bring the entire feature store down. Spark has an inbuilt API, Colisk, which tries to limit the number of executors that try to disperse data at any given point of time. Given we can have some free-form code in Spark, we can also inspect data. What that basically means is, even though we are trying to compute features for lifetime and we are trying to store the snapshots daily, we can effectively diff the data. We can identify which columns have changed, we can identify which rows have changed, and we can optimize so that only the relevant parts of the data really flows through our real-time Cassandra feature store. Additionally, we have been able to write custom metrics and alerting after each of these optimization phases so that if any of the computations ever fail, the system can detect them much ahead of the time before the real-time services try to act on bad data. Now, if you look at the image on the right, it basically shows that on a given day, which is 1st of Feb, an entity got onboarded to our to Uber's platform, and you can see the entire flow. We compute the features to it, the feature got dispersed all the way up to the real-time feature store. Now, for a month, there was no operation on this entity. That is the reason you can see that even that none of this entity never was dispersed again to the real-time ecosystem. Now, when after a month another event happened, that was the only time that the system decided to update the aggregations for this entity. Moving on to the second pillar in our design, this is the streaming aggregator. This basically helps us in computing features which span for shorter durations of time, typically less than a day. All the events that get ingested, they are coming on Kafka topic. So when the event gets ingested, the first thing that happens on the event is event enrichment. What it can be thought of as semantically equivalent to an offline computation. What that basically means is that this system is going to make queries to using RPCs to outside microservices to get the relevant parts of the features. Once the event enrichment phase finishes, we move on to the next phase, which is your application of transforms, which you can think of as lambda functions. Now, each of these lambda function can, in a sense, output a single feature. All these features that are computed, they get processed by our time window aggregator. The role of this time window aggregator is to effectively roll up this feature to a 5-minute granularity and disperse it to Cassandra. Now, moving on to the final piece in this entire aggregation. This is our feature access microservice. What this feature access microservice does, based on the metadata for a given feature, whenever a feature access is made in real time, it decides what part of the feature value should be picked up from which of the offline computations. Now, if you look at the table schemas that we have defined there, all of these schemas are in a real-time feature store. We clearly separated out the schemas. The topmost schema is for a lifetime feature, which for most part is a key and a value. The schema in the middle is basically for our windowed features. The only difference there is we have a clustering key, which is a date. At the bottom part, we have, I'll say, a series of tables which we use to store real-time computed aggregations. Now, when upstream accesses us for a given feature, the metadata service decides, if it's a lifetime feature, it basically has to consult the lifetime table along with the real time, or if these are the windowed features like last 2 days, but the user is also interested in a real-time counterpart, the feature access service does that behind the scenes for it. Now, even though this picture seems very complex, but again, all of these are taken care of in the solution. None of these details are exposed to the outside systems. Now, finally moving on to how this entire system is accessed by our data scientists and analysts. They start creating a query which they need for computing the relevant aggregation features. This query gets landed into a spec, which is on the right side. Alongside the queries, we also take in some additional metadata, which is like a real-time Kafka topic, if there is a real-time feature value attached to it. There is also some metadata around the feature types, the operations, and the feature names. One of the additional things that we do is we also try to take in buckets, even though we don't, I'll say, really compute all these buckets, but what it really does is when we do feature quality, we at least know what kind of features the upstreams are really expecting us to get from. So once they have a spec, they can test the spec. We have built a very thorough infrastructure which can validate queries and even the Kafka events. And once they commit to prod, the different pillars in the solution, they work on relevant parts of the feature, of the spec, sorry, and they try to compute the corresponding aggregations. I briefly mentioned that we wanted to support data scientists as well. So one of the major questions that a data scientist asks is, tell me the value for a given feature, for a given entity on a given day. Now this day is not necessarily today. It can be like any historic day as well. So what that basically means is anytime a spec is onboarded, we have to bootstrap the computations not to today, but to a historic time. And from that point onwards, we try to incrementally compute the feature, and then we try to maintain the lifetime snapshots and the incremental snapshots independently. Now, how do the data scientists really access the feature? So on the right, you can see there is a small image. What it is trying to highlight is if a data scientist is interested in accessing a lifetime feature, they can directly access the partition for that day. The lifetime feature is pre-computed and snapshotted for them. Now, if they are looking for a windowed feature, like in this case, they are interested in having a 30-day window, and the bootstrap date is mentioned as 90. So the system will not just start computations from 90 days back, but instead it will go all the way up to 120 days, so that when on 90th day they are asking for a 30-day aggregate feature, they can get a value for that. Now, even though we store all this incrementally, there is a second job which tries to take the spec and the duration of the aggregation feature, and it tries to output a table which has all these tables joined and produce a single value for them. So finally, moving on to what this system enabled us to achieve at Uber. The first part, I'll say massive scale. We compute thousands of aggregation features on a day-to-day basis for hundreds of millions of entities. We were able to provide a solution which tries to seamlessly combine the offline aggregated computations with the real-time computed values. Given the kind of power that we have derived from different solutions like Hive and Cassandra, we were able to achieve a high QPS. We are talking about several thousands of queries per second, ensuring that our P99s are around 20 milliseconds. We briefly looked at how our onboarding experience looks to the end people. I mean, it's all a spec, and the system automatically orchestrates different components based on that. We have been able to save millions of dollars in computation costs across different aggregation features at Uber. Below is just a comparison of a brute force aggregation for a given feature versus an incremental one. So, seems like we have some time, and we can open up for questions. Thank you, everyone.
Send them to the email.
All right, I think we have time for maybe one question.
Okay.
Anybody?
Or email? No.
Yes.
Hi. I'm trying to set up a similar process at my place, and I was just curious as to how many resources do you need in your team to build something of this scale, and how much time did it take for you to get to this point?
So I can say that we are a team of 6 people, and it took us almost I'll say the first prototype went live in 3 months, but to get to a final crafted solution, I'll say it's been a 9-month journey. Sure.
All right, thanks again. And if you'd like to ask any more questions of our speakers, you can find them after the talk. Let's have one more round of applause.
Thank you.